But Tesla was already looking past the copper wires. He shifted his focus to high-voltage resonance, building massive coils to test a hypothesis that electricity could be transmitted directly through the air itself. In 1901, he began constructing the Wardenclyffe Tower in New York, intending to broadcast power globally. But his design held a fatal flaw. Pumping raw, omnidirectional energy into the earth and sky is incredibly inefficient. The energy scatters, losing its strength almost immediately. The project ran out of money, the tower was demolished, and the dream collapsed. For the next 100 years, that failure defined our physical boundaries. Power would require a wire. Broadcasting energy to the horizon had proved physically impossible. The solution lay in learning how to focus it into a point. The modern solution to Tesla's problem is optical wireless power transmission. Modern scientists have changed the approach. Instead of broadcasting energy everywhere, they beam it with pinpoint accuracy using lasers. In 2025, the U.S. military's Defense Advanced Research Projects Agency, or DARPA, tested this concept at their New Mexico desert facility. This chart details the history of power beaming records. Prior to the DARPA test, the highest documented achievement was sending 230 watts over 1.7 kilometers. DARPA reached a new milestone, successfully delivering over 800 watts of power across a distance of 8.6 kilometers. Spanning 5 miles is a massive engineering victory. But pushing raw distance isn't the hardest part. The true physical barrier to making this technology practical is surviving the chaotic, energy-scattering interference of Earth's atmosphere. To solve atmospheric interference, researchers from NTT and Mitsubishi Heavy Industries ran a highly specialized test. They intentionally fired a 1-kilowatt laser over a hot airport runway, keeping the beam just 1 meter off the ground for maximum disruption from wind and heat. Before leaving the transmitter, the laser passes through an Axicon lens, transforming into a hollow, expanding ring. Traveling through the atmosphere, this ring folds back on itself, overlapping in the center to create a uniform intensity that resists scattering. But even with a perfectly shaped beam, ground heat and wind still create turbulence. This warps the light, creating intense hotspots that can easily destroy sensitive receiver equipment. The receiver catches this energy using a homogenizer grid. When the warped beam hits the grid, hot spots are diffused into an even shower of light. This is absorbed by silicon solar cells, while leveling circuits smooth out remaining electrical spikes. By combining precise beam shaping and mechanical homogenizing, the team extracted 152 watts of stable electricity from a 1-kilowatt laser. That is a 15% transmission efficiency, proving that high-power electricity can reliably travel through thin air. The immediate application for this technology is extreme logistics. Instead of hauling heavy fuel generators or laying miles of vulnerable cables, emergency responders will be able to beam electricity from a central hub directly to remote islands, field hospitals, or disaster zones. In the military and industrial sectors, engineers are preparing to beam power vertically. Unmanned aerial vehicles and drones equipped with optical receivers will be able to fly continuously, operating for days or weeks because they are no longer limited by the fuel in their tanks. Ultimately, this scales all the way to orbit. The long-term horizon for optical power transmission is space-based solar power, using satellites to harvest unfiltered solar energy above the atmosphere and beaming it directly down to electrical grids on Earth. Eliminating the requirement for physical wires removes a primary constraint on where we can build. Infrastructure transitions from a permanent, static utility into a system capable of directing energy precisely across difficult terrain, mountains, or open air. A century ago, Nikola Tesla wasn't wrong to imagine a world untethered by cables. He just arrived 100 years before we had the optical engineering to make it physically possible. His alternating current motor successfully built the modern electrical grid. Now, precision lasers are finally going to cut the cord, turning a 19th century vision into a functional engineering reality.